That actually kind of ties back into sort of my misjudgment of programming from personal experience, right? I mean, the first small portion of your career is very different than the rest of your career. I think we left off with some collaboration, and I think the most important thing that I've learned about collaboration is it's very, very important to have a good error culture. If you screw up, tell people about it immediately. And if that doesn't work out well at work, like if you get, bad treatment for just explaining your errors very quickly and to anyone who's, okay, it's your own personal battle how you negotiate that with your ego. And, that's everybody's personal battle to fight. But if you have to fight other battles at work, leave. Right? The cover-up is always much, 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 much more expensive than the error. And you want to be in an environment that understands that, right? I mean, people in good work environments, in my opinion, and I try and model my company after this, and it's very interesting when, young kids come in out of school and they've been told in school, you have to be right about everything, you have to do everything right, you can't screw up, and blah, 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 and then they come and then they screw up, and I'm like, hey, I do that all the time. I mean, if you're working in software, then you have some non-zero chance of being the only person to ever solve this problem because you actually solved it correctly, right? And if we actually solve something correctly in software, nobody ever has to do it again, right? I mean, it's copyable, it's reproducible. If it's solved well, then it's solved. And so by definition, all the stuff we do all day is either things that people have failed to do correctly before, which is the vast majority of stuff we do all day, or something that no one has ever done before. And we're going to screw up, right? Because no one's ever done it before. I mean, the idea that you're supposed to know how to do this in all of its facets, I mean, know your tools. That's another topic, right? I mean, you should be getting good at the language you use, or the languages you use, and the paradigms you use, and the patterns you use, and the libraries that you use, and all that, and try and get very good at that. But the actual problem that you are trying to solve is probably never been solved before, or the people that tried to solve it the last time failed. And so it's natural to screw things up, to get it wrong, right? And if you realize you're wrong earlier in the process, that's going to be much cheaper than realizing you're wrong late in the process, right? And so you want to work in an environment where that is okay, right? And, we don't always succeed at this because, we screw stuff up, right? But we try at work to try and work on the hard problem first rather than the easy stuff, because it's easy to go, okay, we've got this set of things that we need to do to achieve this goal, and let's go after the low-hanging fruit. The problem is, go after the low-hanging fruit first, and then you realize on one of the hard problems that you misunderstood the problem and have to write everything again under a different paradigm or somewhat different, then all that work you done on the low-hanging fruit is gone, right? So fail fast, and don't be afraid of failure, right? I mean, this should be part of your job, right? I mean, burning money is certainly part of the job of a manager. Whether or not they understand it that way, right? I mean, no decision is usually more expensive than any decision, and there's a statistical probability in any decision that you just burnt money, right? And, that's something that I'm coming to terms with. I think I'm much further along in my sort of personal development as an engineer as I am as a manager. Maybe there'll be a talk about that at some point in the distant future. Maybe not. Maybe I'll never achieve a level where I think it's worth talking about my experience as a manager. But as an engineer, have a good error culture. Try and foster a good error culture. And be the first one to say, I was wrong about that, I screwed that up, whatnot. If you lead by example, usually other people around you get a lot braver, and you can get away from the whole stigma around failing, right? And this is certainly a very important part of collaboration. The other thing that you don't really have in the beginning of your career is field results, right? And, not necessarily just field results, but battle stories and, experience. And the ironic thing is, a lot of the time, this is very hard to glean, right? I mean, maybe you are in a company and you go through some 5-year project. And, I mean, show of hands, who has finished a project and would do it the exact same way again? No hands, right? Well, okay, one, but you don't work in software, so you don't count. I mean, there's always a better way to do it again, or at least you feel that way. Maybe not. I mean, there's not a huge volume of success stories in software rewrites, which is also notable. But if you go through like a 5-year cycle of let's come up with an architecture, let's, a lot of software is on more than a 5-year cycle, right? You may go through half your career in one project. And so you don't have a very high sample size in your sort of gut feeling statistics about what works and what doesn't. And there's a lot of industries where if you do it again, let's go with the tried and true technology that worked last time, right? So you don't do a lot of trying out of completely new things, and I don't think this is particularly healthy. I mean, some companies are large enough, and some people are advanced enough or are adventurous enough to switch projects quite often, and this is probably somewhat healthy for your sort of calibrating your gut feeling about things. I mean, it's sort of part of the whole learning process. You can learn a lot of facts, you can learn a lot of stuff, but calibrating your gut feeling is one of the hardest things to do in life, right? I think this is where open source actually plays a large role, right? I don't understand why people are too shy to put their code on GitHub. Look at my GitHub, it's full of crap, right? That's okay. I mean, that's there for people to critique and to share it with other people and to fail at software architecture because it's hard. And to look at other people's software architecture fails. And yeah, so certainly my advice is to look at a lot of these things. And this has certainly helped me a lot, right? But do we understand what good code is yet, right? I mean, good code has to do with collaboration as well, right? Good code needs to be explainable somehow. Right? Is this good code? Passing a complex number to some function. No, this is not good code. But why? I mean, the problem here is not just the ints, it's that we have some conceptually one thing, a complex number, and we've torn it apart into 2 pieces, right? So this complex number is certainly not going to work in the same way that other numbers work, right? If we wanted to add 2 of these things, then suddenly we as normal programmers have to understand how complex numbers work, right? And I mean, I'd probably get it wrong once, at least. And we have to worry about how to copy this thing. We have to remember, oh, I have to copy both of them. They might get out of sync, and so on and so forth. Right? So we obviously want to tie these 2 things together. Right? This is, some improvement. If we were writing this in assembler, we'd have to think about a lot more things. So the having to think about less things is good, right? This works as expected as a sign of good code, right? But getting rid of the artificial complexity is only sort of part of the problem, right? There's also an inherent complexity. With a complex number, there's actually a very low level of inherent complexity, right? It's 2 things, they work together based on the laws of math. We don't have most of the problems that we have with complexity, because complex number is something that people came up with. It's not going to change very quickly, right? And if we think about other data types, there are things that may change, right? I mean, we wrote a string library in C++, and we wrote it a while ago. I think it predates Unicode. It certainly predates wide use of Unicode. And it doesn't work with Unicode very well. You know, standard string, okay, maybe one could argue it's just a string of bytes that may or may not be encoded in different ways. The encoding is certainly not part of the type. Then we also have member functions on it, like matching and finding and whatnot, and taking subranges of it and whatnot. And this is not very well advised because we're taking subranges of bytes, right? And not subranges of maybe code points. What are we expecting there, right? I mean, this is a very, very complex thing, which we've tried to abstract in a slightly less complex way. And this will not bite you so much if you live in the US, because all of your letters are in there, right? And if you don't, and I think this is probably a problem in Poland, because I got lost once and tried to put in the name of the train station I was at into my phone to see where I was, and it turns out I don't have the letters on my phone. So if you have other letters, then you're suddenly on your own using some other solution for this. And there are a lot of solutions for this. So a string is something that has incredible complexity if you really want to solve the whole problem. Which brings us to sort of trade-offs, right? If you want to solve the whole problem for one person, that might not be the whole problem for someone else. Thinking about sort of changing the laws of physics or changing the laws of that everything's built on, changing the fundamental architecture. If we're in a microcontroller, then, sort of, I guess I shouldn't gang up academia too bad here, but, this whole Internet of Things concepts, most of them include microcontrollers in sort of the edge of the cloud, right, where the data acquisition happens. There's microcontrollers, and most of these sort of models in universities, they have to do with sending JSON packets to and from these things because, people understand JSON packets for some reason, right? Problem is in JSON, you have a standardized thing that, it's standardized to be UTF-8 encoded Unicode, right? Have fun decoding that on a microcontroller. I mean, I believe the smallest that I know of Unicode library that can make any claim of completeness is a couple megabytes. It's not going to fit on my chip, right? So is that good code, that Unicode library? Well, yes, to a certain extent, because it solves a problem for someone. I mean, most code doesn't reach that bar. But it doesn't solve my problem, even though it could, because for me, I don't really care about, lowercase I switching to uppercase I be dependent on where you are, because in Turkish it turns into an I with a little thingy on it, right? Those are special cases that I probably don't care about as long as I'm not switching from lowercase to uppercase. And so I would like a composable Unicode library where I just put in the parts that I need. But that's actually even harder to write, right? Because decomposing things is hard. Right? So, I mean, you could write a Unicode container, which basically is just a vector of raw bytes. And you could have a template parameter that would say what encoding these bytes are in. Haven't gone wrong yet. You could keep building up as long as you are sort of adding small components to the system in a sort of composable manner. You can build up a system which is prone to break at some point because it's it's endlessly complex. Maybe someday we'll meet aliens and they will have new letters, right? Maybe, who knows, current administration will come up with an America First letter. MAGA, one letter. It's something that comes from culture, right? It's something that's changing. Complex number is not going to change very quickly. But if we can build it up of small composable pieces, then the small composable pieces have a much lower probability of not being useful anymore. I might already argue that this struct is still not good code, because first of all, who's content with an int as a complex number? Probably not that many people. You want some kind of floating point something, right? There's another problem with int. Int doesn't quite follow the rules of mathematical numbers, even whole numbers. At some point, it's going to wrap around. So we have a type that's, follows sort of algebraic rules most of the time, except when it doesn't, right? So it's only correct in a certain domain. And maybe somebody might care and might want to see when it rolls over, right? Especially if it was unsigned, then it wouldn't even be UB for it to roll over, right? Maybe we want to templatize this thing so that the user can decide what data type they want to put in there, right? But if we've added a template, I mean, for those of you who don't understand templates, this is just a wild card, right? In there we put a type, which could be int, or it could be float, or it could be double, and everywhere where there's a T, it just swaps it out for that data type. And I can put in this my special int with checks whether or not it rolled over, or whether it will roll over of any given operation, right? There is something like this, or there are several libraries something like this, which kind of differ depending on what. I think the safe int is the one that I've played around with a bit. That would be interesting here, as long as we're working with integers. I'm not sure that there's a safe float, but this means that we also have a requirement on this T, right? If our users are doing calculations with this thing, then they are going to expect it has certain operators and expect some certain semantics from these operators. And so we better adhere to the semantics of those operators, right? I mean, this is going to be a recurring theme. If you write types, which you should, because otherwise you just have fundamental data types, they should follow certain rules. They should be able to, you should be able to put them into categories of types which all follow the same rules, because you have less complexity that way, right? You can reason about a category of things rather than reasoning about all the things in that category singly. So this, there obviously already is a complex in the standard library, right? And standard complex in the standard library is, I think, about 1,500 lines of code, right? Rather than this small struct, because it does a lot more. It has a lot more rules coded into it. It knows how to add itself to other complex. You don't have to know that anymore, right? So maybe you're some kind of non-software engineer and understand complex numbers, or maybe you don't, but you still can add them. You can still multiply them. You can call cosine and tangent and all that kind of stuff on them, right? You probably should understand how this works, but you don't have to. It works the same way as other types do, right? I can call some generic function with it. If I can call this with an int, then I can call this with a complex, and it works, right? So we can codify pretty much all the rules that we need to into a complex, and people have done that, and we should use that. But thinking about sort of our own types, they might be as complex as a complex, or they might be a lot more complex, right? And if we think about sort of a date time class that needs to know sort of date and time and understand time zones, and I mean, this is essentially infinite complexity. How do we go about this? Because if we go back in history, the day of the week it is, in some regions of the world, depended on which religion you had, right? I mean, what do we even take as input to our date-time class? So again, when faced with sort of the endless complexity, we still should be able to decompose it into small pieces that will be true over a long period of time, right? If we look in the standard, then the standard chrono time point, as in date time thingy, that's actually less lines of code. It's about 1,000 in that header. Less lines of code than a complex number. But it also pulls in standard ratio and a few other things. It's composed of smaller pieces. And no matter where you are in the world and how long it's, what religion you have, it has been the same amount of time since 1970 started in Greenwich Mean Time, right? And so that's how chrono works. That's one epoch, it's called. You can even swap them out, right? But if that's kind of the standard frame of reference, and so they've built a sort of a template class where you can swap out many of the pieces, and it builds on sort of things that will continue to be true that are simpler and more abstract, and you can compose them. And this has the advantage that, with the international date line, right? Some point in time, this is my perfect drawing skills. Some point in time, the day starts somewhere in Asia, so they have a head start on us already. The day starts somewhere over there, and sun goes across the sky. That time of day will kind of shift across the Earth, and except for Easter Island that switched around to be on the other side of the date line some years ago. So you can't even rely on it being the next day of the week after every previous day of the week, right? So this is a hard problem, right? If we look at the Easter Island example, it is still the same number of milliseconds since it was 1970 in England, right? It's just the translation changed. So if we model the world in a way that won't break when the world changes and allow ourselves to add sort of composable pieces to this, then we won't break as easily, right? If you're not on Easter Island and don't do business with them, the world still works. And if you do, you have to add one small policy to your code, right? So this might change in the future. I mean, somebody might tell the current administration that the Asians are first, and they'd say, hey, America first. And for the Dutch people in the room, notice the Netherlands second. If you're looking for a bit of fun, there's a video called America First, the Netherlands Second, which explains that inside joke, which is endlessly funny. So if the world changes in the future like this, I hope you don't have to refactor your entire code base, because I hope this doesn't break your assumptions, right? I mean, when abstracting things into composable pieces, try to make most of those pieces rely on the laws of physics, because they don't change that often, right? And as few as possible of those pieces rely on things that may change. And there's an amazing number of things that may change, right? I mean, we have this problem in the standard library where people assumed a lot of things about software architecture, including how long it takes to fetch different pieces of memory and the relative sort of time durations to each other, or whether or not you can have singletons, right? I mean, what problems do singletons pose in a normal system? Say, around my birth. Not much, RAM was expensive back then, and we didn't have very, very long pipelines to it, right? We also usually just had one core. So a singleton was very cheap and probably saved you some RAM because you didn't have to pass pointers around to something, right? On the other hand, today we have multi-core, RAM is super cheap, and singletons break everything, right? I mean, it's not just a performance problem with multi-threading. On alternative kernels or on a GPU or something, you just cannot have them, right? I mean, if we're coming back to the everybody shares a stack paradigm, then how do you synchronize around a singleton? Well, it's your singleton. You can assign it a priority, have one priority lock, have that priority lock disable interrupts in groups, and so on and so forth. But if it's the standard library singleton and not my singleton, then I'm pretty screwed, right? So anything that touches locales will cause a world of pain. It's unfortunate that standard library doesn't document particularly well what touches locales and what doesn't. In fact, there was a proposal recently to, what's called the freestanding proposal. I think it would have gotten a lot more backing if we had called it the get rid of all the secret singletons proposal. And there was an error in that proposal that came up at our EMBO conference because apparently the author and myself overlooked the fact that A to I touches locales. And why? I mean, it's not A to F. It's not like a string to a float where I need to know what the comma is in that language or anything. It's an int. But it swallows preceding white space. And white space is locale dependent because different cultures have different understandings of what white space is. And so it touches locales. And that means we can't use it or anything that uses it. And so, I mean, this kind of comes back to my point of, understand what assumptions you are making about your users and about your code and about the machine you're running on. Because standard library apparently doesn't. It doesn't document this. And yeah, it means that we can't really use that on alternative kernels, right? So how should we be properly encapsulating things, right? And what is encapsulation to begin with? I've been using this term the whole time throughout this talk. And the beginning of my career, the description I got from the book I bought because Alexandrescu was a little too hard in one go. I think it was C++ in 21 days or some other crap like that, right? And the description I got for why one encapsulates things, makes getters and setters for everything and blah, blah, is so that you can swap out how it works later. And that might be true for some people, but I've found that to be a very bad description of why we encapsulate things. Because, depends on what your contracts are with your users when you are encapsulating something. I mean, just making everything a getter and setter doesn't mean that you have encapsulated yourself in maybe the time domain, right? And you are pretty constrained about sort of what you can actually change under the hood later. Right? I think a better description of why we encapsulate things. We encapsulate things so that we can so that we can enforce invariance, right? Now remember how many different states your system can be in, theoretically. If we have a data structure and anyone can touch it, well, that's not a gigabyte of data. It's maybe, 10, 15 ints or something. That's still a huge number of possible states that thing can be in. And probably most of them are not valid state, right? I mean, with a complex number, we actually can cover the whole field, right? With my protocol ID, there were only very few numbers that were actually valid numbers there, right? I may have an object that contains a pointer to a heap, a vector, right? Vector, small object, pointers into the heap, I can assume the invariant that the pointer to capacity is always the same or larger than the pointer to the end, and that the pointer to the end is always the same or larger than the pointer to the begin, right? And that if I have a pointer to begin and it's not null, that the others are also not null, right? If the user can touch those, I can no longer assume that, right? So I basically enforce a certain subset of all states that this thing can be in. And those states are states that I consider valid that I'm expecting, right? And we can actually use this in our own code, on our own code bases, right? If I have a pointer that I'm checking to see if it's null all over the place. Actually, that's kind of a dead horse. Why don't we beat something else? Maybe I have SQL in my program, right? And some SQL searches come from the outside. And the some that come from the outside can contain code injection, right? Can contain attacks and all sorts of stuff. So I should be very, very careful to check those before I actually unleash them on the database to make sure that they don't have anything terrible in them, right? So I could check whenever I use one, and that's probably a lot of places, right? I might be checking a lot of the ones that came from inside my program, which can be assumed to not contain a bunch of hacky stuff. But that's probably the wrong strategy. I'm probably checking too often in general and checking one time too few in practice, right? There's probably still some way of getting code injected into my program, because if I'm trying with programmer discipline to check all of them, then that's probably not going to work out so well. So how should we do this, right? I mean, we can codify, we can enforce sort of in the type system whether this is a piece of SQL which came from the user, or whether this is a piece of SQL that's safe to submit to the database. Make two types. They're convertible to each other. When you convert, you check, right? It means that if I forgot to check once, that I didn't forget to check, right? I can't actually physically get it into the database without checking. And there's a famous quote by someone that I can't quite pinpoint right now. It's very hard to ship code that doesn't compile, right? And we can use the type system to enforce this. And this is super super useful. Another sort of example of going beyond sort of classic encapsulation. We can encapsulate a lot more than just data. We can also sort of encapsulate intent. We can add rules to things. There was a company or a friend of mine worked in a company where they had the problem of people misunderstanding how to fetch and filter data from a database, right? They'd fetch things, and then they'd limit it to a certain number of things, and then they'd filter, which is the wrong way around, right? And if you want 1,000 data sets, you don't go out and get all the data sets, then cut that down to 1,000, and then filter. Because if the first 1,000 don't match your predicate, then you get 0. It's definitely not what you were expecting. And if in your unit test, the first 1,000 do match your predicate, then your unit test passes, right? So after this happened a couple of times, somebody had the bright idea of making a handle to a database result, which you can call some function on, like filter, like I think they called it trim or something, to trim it down to something smaller. And when you call one of these member functions, you get another object back. And that object that you get back, you can continue to call things on, right? So you say query, and then you say filter, and that filter will give you an object back, which you can trim. If you do it the other way around, if you request trim, that object that you get back from that operation, you cannot filter on that anymore. It doesn't have the member function, right? So I've encoded rules about my type, which allow my colleagues to not shoot themselves in the foot. Right? This is more of sort of this encapsulation of intent, if you will, right? Or encapsulation of documentation. I mean, there's another. Well, probably one of my favorite quotes of all time is Bjarne Sturstrup on comments, and I think it's actually controversial whether he did or did not say this, but people claim that he said the compiler does not read comments, and neither do I. And there's a lot of truth to that. I mean, documentation often gets out of sync with your code. And, it may help you a bunch of times, but when it's out of sync and says something that's not true, that can cost you a lot of time. And on the other hand, this database example, well, that's in code, so the compiler checks, and that is true, right? So, the implementation details of a lot of these sort of more complex abstractions may be scary, but you only really need one or two people on the team that understand them well. I mean, a larger team, maybe a few more. Maybe you have a library department in your company if you're large. This pays off a lot, in my experience, right? I mean, you build a lot of these things for your team to use. You can pass knowledge to them, and they don't even know it, right? I mean, you gave them a type which can't do X. Well, now they know not to do X, because if they try, their compiler will yell at them. So coming sort of towards the end of this talk, it took me a long time to really understand what architecture is, right? I mean, people always say you have to get the architecture right, right? Well, what does that even mean? And if you look at books on architecture, well, I usually always come back to like Euclidean geometry or and yes, that is a very big part of architecture, but why? Right? Why is that part of architecture? Sort of for myself, my understanding of architecture is the part of your program that's really hard to change. Right? Architecture is part of the program that everybody sees, right? Everything builds on the architecture. If you get the architecture wrong, you're screwed, right? So maybe small encapsulated portions of your code, right? Where, the world just sees this interface, and then I have my little world behind this interface, and maybe I can code dirty there, and it's not a problem, because I can refactor that faster, right? I mean, that little piece of the world, that is more like the projects that I did at the beginning of my career when I was just playing around, right? But the architecture that connects everything together, well, you can't change that, right? So you better go at that with some sort of more formal means, because there's actually a whole nother discipline that comes up with systems which don't break very often, right? It's, math and physics and some of those guys. And that's why you actually come back to Euclidean geometry. That's why you come back to type theory and these kinds of things in architectural questions, because those are sort of the corners of academia, or the corners of sort of knowledge where we actually are good at these things. And so, part of architecture, for example, are vocabulary types, right? Everybody know what a vocabulary type is? Right? So it's a type that goes sort of across and through all of your system that everybody's interacting with. I mean, a date time is probably a vocabulary type. String is probably a vocabulary type. But my internal state struct thingy-majigger is probably not a vocabulary type. It's local to your part of the program. And chances are you have way more types in your code base than you actually need, right? I mean, everybody came up with their own, right? They're probably not composed out of smaller pieces. But theoretically, if you were to take all of the types in your code base and try and find a much smaller set of composable types with which you can express all of those types, you would probably be very successful. You will get a lot more bang for your buck if you do this exercise in vocabulary types and keep the number of vocabulary types in your system very, very small, right? And very, very generic. errors are also part of architecture, right? At least in most cases. They propagate across modules. They're part of interfaces. And sort of the fundamental, or the fundamentals under errors, you know, the first divide and conquer thing that you can divide is essentially every error is either a programming error or an input-output error, right? Somebody either gave you bad data or you screwed up as a programmer. One of the two things is happening, right? I mean, that somebody may be the database, that may be, you know, something else, but you know, we kind of ignore the probability of solar radiation flipping bits in our RAM or things like that, right? I mean, something once being different is probably just an anomaly. We kind of assume that the RAM works, that the system is sound, that you know, if we get an error, then somebody did not expect that value in that place, even though it was valid user input, or you know, some result of valid user input down the chain, hence a programming error, or it is input from the user that is not correct, right? And programming errors, or programmer errors, tend to be easier to fight with contracts in the type system, and user errors tend to be easier fought at the boundary. So if I'm trying to sort of scale my engineering potential, then it's probably a good idea to get a sense for what architecture means. Even if you're not the architect on your team, you're taking part in sort of this architecture, right? I mean, there are books on sort of very fundamental knowledge about systems of types and whatnot. I mean, what does it mean for a type to be regular? If you can't answer that, then find a book on it, right? What does it mean for a type to be orderable? Why is that important, right? In order to deal with data in a generic manner, it probably needs to be orderable most of the time, right? If I want to make a fast lookup container, you know, if I don't understand what the thing is, if it has a less than operator, I can do that. If it doesn't, it'll be harder anyway, right? And it'll be unexpected, because pretty much everything should be orderable. Are all of your types orderable, and do you know how they are orderable, right? Homework. Probably the least talked about portion of this, and sort of the closing idea here, is that being a good programmer is understanding what you are yourself, right? I mean, it's the end of the day, your brain is a bag of chemicals that evolved to do something very different than write software. So, I mean, some of us do better with procedural programming, some of us do better with functional programming, some of us do better with different paradigms. But I would argue that you're probably not lighting up all of the infrastructure in your brain just with one of these paradigms, or just with, you know, consciously understanding how your software works, right? I mean, this is an example that I had luck of the draw, day before yesterday, I think it was. We're walking around, and one of my coworkers noticed this license plate holder, right? Audi Centrum Bochum. This happens to be a car dealer in my hometown. And, okay, no keyword, Audi Centrum Bochum, no. I mean, I work with some weird people, but they're not that weird. They don't go around consciously looking at license plate holders, right? There was some sort of pattern matching infrastructure in his brain that just noticed this. And it was from like 20 feet away, right? So we actually have a whole lot of pattern matching infrastructure in our brain that just, in sort of subconscious, now and then when there's a good match, says, hey brain, this is weird. Check this out, right? I mean, I have some pattern matching infrastructure in my brain that takes general conversation and makes bad jokes out of it. It drives my coworkers crazy. But we also have, you know, a lot of pattern matching infrastructure that sort of tries to predict what's going on, right? And if we unleash that on this piece of code, then we're probably going to get some false positives here, because there's obviously a bunch of problems with this code, right? Can I reason about this code locally when I look at it? Well, first of all, I didn't initialize that, right? So I'm going to get really weird results. This actually happened to a colleague of mine a couple of days ago. Luck of the draw, right? Also has a performance bug, probably because maybe the optimizer can't deduce that the size of the vector can't change, because maybe it's coming in from somewhere else where it might be changed. Maybe it doesn't understand what's happening inside foo. Maybe we could be pushed back into it and the optimizer doesn't understand us. We also don't understand what foo is doing with I, right? Maybe it's just indexing into the vector. Maybe it's changing I, right? Maybe it's taking it by reference and changing it, right? This is very hard to locally reason about. I mean, somebody could say, if I equals 42, then I equals 0 again, and it's an endless loop, right? It doesn't happen very often. The pattern matcher in your brain is going to say, that's not going to happen. I understand that code, that's not going to happen, until it does, right? Comparing that to this piece of code, first of all, your pattern matcher has a name. It says, hey, that's an accumulate. I know what that does. Who knows what that does? Good crowd, most of you. Learn your algorithms, learn your patterns, right? And if I go over my old assembler, I don't find any accumulates in there, but I do find a lot of patterns in there that have names, right? I mean, I certainly did a bunch of strategy patterns, had some state machines. I mean, I called them hooks because I didn't know what to call them, right? So I hooked into things for my strategy pattern. And my states were called steps and whatnot, but it's the pattern. And I could have talked to other people a lot more effectively if I had known the names of these patterns and the names of these algorithms. And in this case, I can read other people's code a lot better if I see the name, but it's not just the name. I know, and my pattern matcher knows, that I am not changing this vector, right? Because accumulate doesn't give the function object non-const access to the input range, right? Or to the input iterator element, right? I also know, I mean, I'm also quite constrained on what sort of better foo. I mean, we need to be able to, we need a binary predicate and not a, 3 different things going together, assuming this is doing the same thing as the for loop did, besides all the undefined behavior. So if I program in sort of higher level concepts, it actually helps me collaborate with my colleagues if they've also put in the effort to understand these higher level abstractions, right? It also probably helps the optimizer, because the optimizer can reason about a lot more things than just in my for loop, right? Because the optimizer knows that better foo can't change I because there is no I, right? We come back to sort of what is good code. One final addition. Is this good code? Well, maybe not because of the int, but let's ignore that. It really depends on what foo can do, right? I mean, is this a complex or a non-complex thing? A good way to judge that is, could I fully unit test this thing, right? If it is an int, and if this thing doesn't touch secret singletons, then it is a pure functional function, and I can unit test every state, right? If it does touch something, then this is endlessly complex, right? So, if we want to reason about complexity, knowing that things are pure functional is a huge advantage. Sort of in closing, sort of my conclusion to all this, if I were to sort of try and put it in a sentence, would be that better code reduces the complexity without reducing functionality, right? I mean, at the beginning of my career, I actually, when I was first starting out with C++, I was able to look into the code base of the MP3 compression algorithm that was written by the guy at the Fraunhofer Institute, which came up with it. And I thought, oh my God, that guy is an insanely good programmer. Look at all this complexity, right? Look at all these things he's doing with all these void pointers, and I was impressed, right? And today I think when I look at a piece of code and it's super simple, right? I think, wow, that's a good programmer, right? Because they took all that complexity away. I mean, the guy that did the MP3 algorithm certainly was good at understanding how, people hear audio, because it's definitely not the same way a microphone measures it. So they were able to write a very good compression algorithm with that knowledge, but the code, probably not that robust and probably not that bug-free. So, you know, if you see something that's just endlessly complex, try and break it up. Try and make it into composable pieces, right? Try and look for the sort of the underlying information and find people that do this for a living, right? Sean Parent's here in the front row, or Stepanov, or other people. Ben Dane's actually sort of a new addition, in my opinion, has some very sort of fundamental knowledge on these things. And maybe you have unending complexity, or maybe it's just a rotate, right? As a callback to one of Sean's talks, right? Maybe it's just something that you haven't come up with yet, because there's not a lot of algorithms that haven't been invented yet, right? If you invent one, probably get an honorary doctorate for it, right? So, yeah, that's sort of my brain dump. I hope it's useful to you. I would like a lot of feedback on this talk, because it's kind of the first talk I've done in this sort of format. I usually just do very, very high-level experty talks, and they're actually a lot easier to do, because if you screw up in an experty talk, well, it was an experty talk, right? It's okay that you were wrong about that one thing. You screw up in a fundamental talk, it's like, ha, look at that guy, doesn't know the fundamentals. So there's a little stigma again around knowing the fundamentals. So, questions?
Just very briefly, one question. Mm-hmm.
Just yell. Okay. I saw you program microcontroller stuff, and my question is, you have kids?
Yes. 2 of them by now.
Okay. Kids are, let's say, when they're born, they're pure hardware.
Yes. Well, that's debatable, but yeah.
Did you, maybe this is not program related, but did you, I don't know, extrapolate your way of thinking about programming with your kids?
So the question is, does Odin screw up his kids with whatever he's thinking about programming?
Well, maybe. Yeah, no, there's a funny story and then some sort of very sort of personal opinions about this. It's funny, at least I very seldom feel that I'm right about something, especially in my professional career. Like, you know, I've been wrong about almost everything I've ever thought, so what are the chances I'm right about something, right? And that's probably true for most everyone, depending on how you sort of deal with that. I mean, if you were ever right about anything, you couldn't improve anymore, and that would be boring, right? But somehow I feel right about all of my just kind of pulled out of a hat ideas about parenting, which is weird. But the funny story, when my son was very little, you know, he had bad colic, and so he'd lay on my arm and lay on his belly, and I'd walk him around, so he'd be kind of moving, which helps them sort of deal with that. And you know, being a nerd, I had a laptop on the other arm and was watching conference talks, right? And so his babysitter, when he was about, you know, 1.5 and just had maybe a vocabulary about 20 words or something, and you know, she had spent the whole day with him, and then you know, was saying bye, and she says, "Say my name," right? She's like, "Oh, he's gonna say my name. He's gonna say my name," and he says, "Compiler."
So the answer is yes. So the one and only Stackenite Udarnik Odin Holmes.